Okay, welcome everybody. So we're going to let people continue to trickle in. It gives me great pleasure on behalf of the Data Analytics Research and Teaching Committee. Where's Ting? Ting, where are you? There's Ting. Ting chaired the committee with a lot of faculty in the committee, and David has been gracious enough to take time from Boston, visit us. And for those of you who know David, you know that he's had incredible number of different roles that he's played as part of the community, and in particular, his current role is as editor-in-chief of Management Science. And one of the things I asked David is some fun fact, and so those of you who are looking to the next conference he's organizing, it's going to be on a boat, and it's going to involve scuba diving. So that's what he's told me. So be on the lookout for that scuba diving effort, with the papers being presented underwater. Is that right? But all kidding aside, I mean, David is the professor of engineering systems at MIT. He's a premier thought leader in the supply chain management area. And one of the things that's interesting, and is something that faculty here and lots of faculty are looking at, is the link between data, model building, etc., and the room that it affords for some interesting new research and contributions to research. In particular, David talks about applications to Groupon, Rulala, and B2W Digital. And these are all examples of the kinds of things we hope can be something that faculty across different areas can sort of start working on. So without further ado, David.
Thank you for the nice introduction. Thank you for inviting me. I'm going to talk about some of the data-driven research that I have been involved in over the last 4 or 5 years. It's appropriate to start this talk by describing the infrastructure at MIT that allowed us to do this type of research. At MIT, I lead a center or an alliance in business analytics that bring together MIT faculty, MIT PhD students, together with about 25 companies to focus on some of the most challenging problems that these companies have by bringing together their data, models and algorithms to make an impact on bottom line. The alliance is cross-industry. We have some companies in oil and gas, some in retail, financial services, airline, and it's cross-functional. Some of the projects focus on revenue optimization, some of the projects on predictive maintenance or social media, process optimization like supply chain optimization is an area that we focus on. And you can see here companies that have been involved in our research. For instance, from the software industry, companies like Oracle and JDA. With both companies, we have developed software. In the case of Oracle, it is implemented as part of their technology. Companies like Alibaba and JD.com. I think my postdoc, Shinshan, visited you a couple of weeks ago. He showed some of the work that we are doing with Alibaba. Companies like Starwood, which is the hotel chain, that is now part of the Marriott, where we focus on their pricing. Airline carrier, for which we develop customized pricing strategy, but not for the price of the ticket, but for ancillary product. And so you go on some of these airline and you decide whether you want to buy a ticket, say from Indianapolis to Boston. Once you made that decision, our system kicks in and suggest all sorts of ancillary products. The first one will be priority boarding. And the offer that Anant will get will be different than the offer that I will get. because they know how much I paid, they know my history, they have a lot of information about the individual that allow us to customize different products. At any point in time, we have a dozen of projects running in parallel. A project brings a specific company. It brings an MIT faculty and 1 or 2 PhD students to focus on a specific problem that the company has. The expectations are that the company will discuss with us a specific problem, will provide data, clearly under an NDA, and that if we are successful, they will engage at least in a field experiment to test the effect. Or hopefully, this will be a technology that is running continuously within the company infrastructure. As you can see on this list, some of the companies are part of the new economy, online provider, but not everybody. There are some companies that are CPGs that are part of our alliance, where we have done a lot of work on optimizing some of their pricing strategy, especially promotional offers that they have. So at any point in time, we have a couple of projects running in parallel. Here are a few examples. I'm splitting the different projects into 4 categories. At the center, I have what I call foundations, like linking analytics to business performance. The second category is around risk analysis, for example, reducing false positive in fraud detection, a technology that we develop for the state of Massachusetts. Holistic risk assessment, this is an analytics that we develop for a large insurance company that allows them to identify how much risk they face with a new client and what kind of product, what kind of offer to give the client and at what price. There are a couple of examples in the retail space. For example, using social media information to improve supply and demand forecasting. And finally, the last category is industrial operation, optimizing capacity and service level for a large high-tech manufacturing company. This is an interesting project, the last one, improving mining operational performance. This is about what is called in the public and popular literature, IoT. So this is work that we have done with one of the largest mining company in Latin America, where they extract iron from the ground, and the iron goes through many steps in the manufacturing process until they have the finished product. The problem is that when it goes out through the manufacturing process, it takes a long time, and at the end, they have to test the quality, and the quality is low, they have to destroy the entire batch that was produced. The question is, can we use sensor data in real time, providing data about different parts of the manufacturing process, and there are about 2,000 sensors that generate data every 5 seconds. Can we use this data to predict what will be the quality of the product coming out of the production line maybe 15 hours later? Because if we predict that it's low, then we also would like to see, can we recommend why it's low? And if we can recommend why it's low, it suggests to the operator what to change. And so this is MIT, basically algorithm running in a control tower setting, day in and day out, predicting what the quality will be, and when the quality is low, suggesting changes. So here I'm going to talk about one example, but before I jump into the research itself, it's appropriate to highlight why we have this opportunity. And I would say there are 3 trends that we are all familiar with. I'm just trying to set them correctly before I go into the analysis. The first is digitization, right? not only companies a lot of internal data, they have also a lot of external data that we can combine with internal data that allow us to learn about, for example, consumer preference. Some of the data is structured, a lot of the data may be unstructured. The second is the analytics, and when you talk to companies, everybody's using some data and some analytics. I'll focus here and define here what exactly I mean by the analytics. And the last element is the ability to integrate data and analytics to automate processes. And a lot of the interest that companies have in this space come from the requirement to automate processes, because they will not talk about this, but what they mean is, I can automate processes, I can do the same things that I'm doing, even better, with fewer people, right? Typically, we don't like to talk about this, but that's a lot of time what's behind the focus on automation. So what am I referring to when I talk about analytics? One intuitive way to think about analytics is to think about this framework where on the x-coordinate I have how easy or difficult it is to do the analytics, and on the y-coordinate I focus on the value to the organization. And there are 4 levels that I'm focusing on. Descriptive, it's just looking at the data and trying to figure out what happened. Every company is doing that, there is nothing new about it. The second level is diagnostic. Not only tell me what happened, but try to explain why did it happen. A little bit more sophisticated. Still, there is nothing new about this level. The top 2 levels are where we are going to focus on. The combination of prediction, predictive and prescriptive analytics. In predictive, I'll focus a lot on machine learning, and in prescriptive, I'll focus on optimization as a way to change behavior, as a way to allocate resources, for example, better and improve performance. And so you think about the focus of this talk as emphasizing the top 2. In some sense, what I am going to do is use data to achieve 3 objectives. The first is to understand behavior. Just look at the data and try to explain why people are doing what they are doing. The second is once I have that, try to use this understanding to predict behavior. And if I can predict behavior, I have an opportunity to change decisions and optimize pricing or ads or inventory in the organization. That really is the focus. Let me pause here and make an observation. There is a lot of excitement about data and analytics, and I think some of you heard me, at least the people that attended some of the conferences in Portugal say that. There is a lot of excitement about data and analytics in popular media, but in reality, there is not a lot going on. That's the hard truth. In fact, the way I say it, this is much like, and take it with a grain of salt, this is much like sex in high school. What do I mean by that? Silent. Everybody is talking about this, nobody is doing anything. The more that some members of the class talk about this, the more that others talk about this. Same is true, a lot of talks, but I would say not a lot of action. One reason for that is, and maybe I'll spend time at the end, one reason for that, there is a lot of resistance to what is done with machine learning and analytics. Part of the resistance comes from, here you have a black box that recommend a decision that is different than the intuition of the decision maker that have been using his intuition and experience and gut feeling to make decisions for 20, 30 years. And now you are telling him or her to do something differently, but you cannot explain why. Does this make sense? And it's hard to convince somebody who's been extremely successful one way that we can do better in another way, but we don't know exactly why the machine is recommended what it's recommended.
Maybe I have one question. So this framework, you're talking about decisions such as pricing and inventory decisions. Does this framework work for long-term decisions, strategic decisions? Or is it...
Yes, so for long term, there are other challenges because you do it once. So it's not clear, for example, what is the learning that I take in the machine learning. I'll talk maybe toward the end a little bit about strategic decision, but it's a little bit different than this. And I will say that even tactical decisions are more difficult than what I'm focusing here. Here I will focus on situations where I can do lots of experiments. And maybe there are business constraints that say you cannot do too many, but I can do experiment. With strategic decision, nobody, as an example, is going to change its supply chain one way, say, oh, it's not working, let's change it another. Right? So I'll come back to that a little bit toward the end.
So David, you mentioned this notion of thinking of the output of machine learning as a black box.
Yes.
But then earlier you mentioned understand behavior and predict behavior. Shouldn't that be applied to the machine learning so you can understand behavior and predict?
That's what I want to talk about. But the point I'm trying to make is that if you apply the black box without taking the domain knowledge into account, you have two challenges. First, nobody is interested in doing something that they cannot understand. And second, you cannot even explain why the results are inconsistent with what the intuition suggests. And I'll show one example of this now. Okay, so I'm going to focus on the revenue management type of applications that we worked in, and then try to take it and see what learning I have in general for this area. So I am going to report here work with 3 different companies that at least one of them you know very well, Groupon, right? How many of you purchase any coupon from Groupon? It's good. I have never purchased anything. But I know when you do that, the price you pay comes from the algorithm that I'm going to describe. We sell, Groupon sell every day thousands of offers, thousands of new deals. Demand prediction is very difficult. They used to collect a lot of data on the fly, but never change the price or optimize price once they introduce a product. And the product life cycle is relatively short in the sense that they introduce a product, the product stays on the website for 4 days. At the end of day number 4, you can still find the product, but the product is moved to a secondary page, so it takes more effort. So this will be one example we'll focus on. The second is a company called Roulala, which is, how many are familiar with Roulala? It's an online retailer, but it's not a general online retailer. It's in a flash sale business. In flash sales, online retailer offer a product for a short period of time, say 24 hours, at a deep discount. And once the event is over, the discount disappears. There are multiple companies competing in this space. Here are some examples. Roulala is based in Boston. Guilt is based in New York. It was acquired recently. Zulily is based in Seattle. This is a European company. And there is a very successful Chinese company in this space called VIP. If you go on Roulala website, you see multiple events running in parallel. And the website will say for each event how much time you have until the event is closed and the discount disappears. Suppose I am interested in women running shoes. I click on this event. I see the type of style. For each style, you can see Roulala price and a discount and relative to the recommended price by the manufacturer. and you need to decide whether you're interested in any of the styles. Suppose you are interested, you click on the style and you see what are the available sizes, and then you make decision whether or not you are interested in buying. The key for our discussion is operations. The way they operate, they decide what to buy from the typically fashion manufacturer, fashion designer, like Ralph Lauren or Louis Vuitton. The item will arrive at the warehouse, and then they need to decide what event to use, when to sell the product, and at what price. This is the first time they sell the product. They have no historical data. They just use before us cost plus, and hope to sell everything during the first event. If they didn't, then the product has to stay in the warehouse for 6-7 months until the next time they can sell the product. And the reason they need to wait is because the fashion designers, the manufacturers, do not want their product to be discounted too frequently. And so it's very important to optimize performance during the first event. The problem is this is challenging because I have nothing about customer demand for this product. And the last one is B2W. Think about B2W as Amazon of Latin America. The same company like Amazon, the size is about $45 billion, where they sell multiple products online to the customers. The headquarters is in Brazil. I'll talk a little bit about what we have done. So what I prepared here are 3 stories. The first is the work that we have done with Groupon, where we do sequential learning and optimization. We start focusing on learning, and then we switch to optimization. I will explain why this algorithm, which was very powerful in the case of Groupon, was not powerful enough for Ulala, and why we had to switch to what I call combined learning and optimization, where we simultaneously learn and optimize at the same time. So this will be applications of machine learning and optimization for pricing product by product. The third topic will be different. This is what, so we optimize price the way I'm going to describe for Ulala for companies like B2W. But at some point we found an interesting challenge, which is bundles. And the question that we focus on: can you use bundle information without experimentation at all to decode customer sensitivity to price? Does this make sense? In the first 2, I'm going to experiment, right? Different experimentation in different applications, Ulala versus Groupon. I'm going to do experimentation. Question is, if I cannot experiment at all, is there a way to decode something about customer sensitivity to price, product by product? And I want to show you that bundles include huge insight that we can take advantage of. All right. So, and this is work that was done with B2W. And again, I'll talk a little bit about data-driven research in general. So let me start with the Groupon. And this is the same slide that I showed before. Every day they introduce new deals to the market. And when they introduce a new deal, of course, they know nothing about customer demand. And they, before us, used to do a single price, and then hopefully hope to improve to maximize expected revenue during the 4 days we are focusing on. So here is the model that we developed. So, and I will start by presenting the model, then a little bit of theory, and then spend some time about practice. And my objective is to show that there is an opportunity here to develop approaches that are supported by both theory and practice. That's really my interest in the 3 examples I'm going to highlight. So let's start from theory. The model is extremely simple. We have a single product. with unlimited inventory. These are coupons, so replenishing coupon is not an issue. Customers arrive on the website one at a time. The platform can optimize price. We may choose price from an interval or a discrete set. Question is, what do we know about customer? Right? So I'm going to assume in the theoretical part of this section that somehow I have k possible demand functions. Here they are. Think about demand function, for example, demand function I as the probability that a customer will buy a product at a specific price peak. Does this make sense? And somehow I generate this k demand function. Now, I'm going to make another assumption that the true demand function is one of these things. So you can imagine there are lots of practical questions. How do you generate the demand function? How many demand functions? And how do we even know that the true demand function is part of this? But for the purpose of the theory, we make all these assumptions. Okay? And again, I'm going to show you the story assuming binary demand, right? Customer comes and this is just the probability of whether they accept or reject our offer for the product. All the results are generalized for general demand function. So here is the idea. I'm generating k demand function somehow. In this case, I'm just assuming linear, but I don't have to assume linear demand function. Demand function I is just the probability that the customer will purchase the product at price, at a specific price P. And we are assuming that the true demand function is somewhere among these demand functions, but we don't know what it is. So given this setting, our algorithm is extremely simple. We take the planning horizon and we partition it into learning, T1 units of time, and optimization. We learn in the first period about customer demand, and then once we decide, okay, we learn enough, we switch to the final part. Let's start thinking about the trade. The trade-off are intuitive. If I learn for a long time, if T1, in the case of Groupon, it's 4 days, the entire horizon is 4 days. If I learn for 3 days, I will have a good understanding of customer demand, but there is not enough time to optimize. And the reverse is also true. If I learn just for a few minutes, I will have an approximate understanding of customer demand, but I have a lot of time to optimize. So the question is how to learn, how long to learn, when to switch, and how to adjust the final price. So what I'm going to show you is extremely intuitive. There is nothing surprising about this idea. I'm going to start with the learning price, right? Here's the initial learning price. And if we go back to the slides, the question I will ask you is, I have two prices here, P1 and P2. Which one do you prefer for the learning price? P1 or P2? And why P1? Because if I select P2, they are all the same. So I cannot distinguish within the different demand function. So if you think about learning price, theoretically what I want is to select a learning price where we distinguish between the demand function as much as possible. Later on I'll tell you a little bit about the business constraint. But from the theory point of view, I want to select a price for the learning part where we decouple, we distinguish between the different demand functions. So I observe sales during the learning period, and then I ask a simple question. Given this level of sales, which demand function is the closest to approximate this level of sales in expectation? Very simple test. Suppose it's demand function I drop all the other demand function. I treat I as if it was the true demand function, and I optimize price based on this demand function. Extremely simple idea. Now, what can we say about this algorithm? Suppose there are T customers that are arriving. If I use fixed price, which is what they used before, and I look at regret. What is regret? Regret is the difference between revenue achieved by an oracle that knows the true demand function and the revenue achieved by our algorithm, whatever algorithm we apply. If we focus on regret, under fixed price, regret is growing linearly with the number of customers. But if I switch to the one learning price strategy that I just presented, then I can cut regret from linear with T to logarithmic with T. Now, you can ask another question, what if I use two learning periods? I start with P1, then I learn. Then I say, okay, let's use P2 as another learning and so forth and so on. We know that if you learn M times, for example, twice, then the regret goes down as a function of log of T indicated, iterated M times, right? And in fact, this is best possible. Nobody can come with another algorithm whose regret is better than this regret. Now, our partner at Groupon were data scientists, people with PhDs in physics and mathematics. They immediately realized this function. They realized that if I look at regret as a function of how many times I learn, how many price change I implement, that there is a decreasing marginal benefit. Right? The biggest impact is achieved with the first learning price. So they said, guys, from customer serviceability point of view, we will allow you only to change price one time. And so the question is how effective our analytics is going to be. So, but by the way, they said, not only you can change price one, there are many business constraints that your algorithm is not taking. I said, what are you talking about? I said, here are the business constraints. First, you cannot decide on the learning price. The learning price, which is the initial price, is negotiated between Groupon and the vendor. So this is an input to your algorithm. You cannot control it. Okay? Then destroy our objective of separating the demand function. Second thing that they said, you cannot just come up with any price. If your algorithm recommends an increase in price, we are not interested. If your algorithm recommends a decrease in price less than 5%, we are not changing anything. And if your algorithm recommends a price greater than 30% relative to the original one, cap it at 30%. So we have a very short window where we can optimize price. Does this make sense? And then they said, by the way, the vendor receives a fixed share. We said, what do you mean? They said, look at this example. This is a coupon for a Japanese restaurant in the Boston area. You buy it for $17 from Groupon and you redeem it at the restaurant for $30. This $17 is split between the restaurant that received 10 and Groupon that received 7. If our algorithm cut the price from 17 to 15, the restaurant still gets its 10. Groupon share goes down to 5. So now we have a conflict. From the vendor point of view, reducing the price is not bad because they will get more clicks. But from Groupon point of view, this may be an issue. So Groupon is saying we need to make sure that both we are doing well and our partners are doing well. Does this make sense? And then they said, all is good, but how do we generate the demand function and how many demand functions we need? And so the next step in this approach was to develop the process to generate the demand function. And the first thing we did a lot of experimentation with many deals using two prices. Because remember, they don't want to change the price more than one time. So I have only two prices. We did a lot of experimentation for lots and lots of deals. I have two data points. The best I can do are linear demand functions. Remember, the theory allows us much more sophisticated demand functions, but the data only suggests basically linear demand function. And now, what I have is the following. I have thousands and thousands of deals from the experimentation, each of which is associated with a linear demand function. Now comes a new deal. What are the demand function and how many I should use? So I look at the features of the new deal, and out of the thousands of new deals, I select a subset, about 800 or 1,000 deals that have similar categories, similar discounts, similar area, and so forth and so on. And I plot these 900 or 1,000 deals on this figure. What is this figure? For each one of the 900, remember these are historical deals, and dot here will have an x coordinate that represents the demand of this deal in the linear function at the price of the initial learning level. Does this make sense? And the y coordinate is just the slope of this deal, right? And I have this huge set of dots that I'm going to cluster into groups that have similar characteristics. For example, using k-mean clustering, I'm generating 3 clusters. The center of gravity of each cluster is by itself a demand function. These are the demand functions that we use. And we developed this framework, and we gave the tool to Groupon, focusing on k equal 10, generating 10 demand functions. We were fairly certain about our techniques, and we were just letting them run the analytics and waiting for the good news, but the good news never came. In fact, when they called us, they said, this is terrible, it's not working. We knew that the theories, that the method, the analytics should be very effective, but we suspected that the number of demand function may be a problem. So the question was, how do you optimize how many demand function you need? So what we decided to do is to use cross-validation. So remember, I have thousands of demand functions. I split them into training and testing. 20% were in the testing part. And I treat each deal in the testing as if it was a new deal. What do I know about these deals in the testing? I know the initial price, P1. I know the final price, P2. And I know what was the sales under P1 and what was the sale under P2. Does this make sense? So I start looking at a specific new deal whose initial price in P1. I use the k-mean clustering to generate k-demand function. For example, 30 demand function, right? Now that I generated the 30 demand function, I know what the sales under P1 was. I ask my learning and optimization algorithm which demand function you would focus on. Well, it says demand function I. This is a demand function that my algorithm will think is a 2-demand function. I plug P2 into demand function I. This is what my algorithm will think that the demand is going to be under P2. I know what the true demand is, I can compare the two. Does this make sense? And they said, guys, here is our matrix, use QPM, which is like the probability of purchase, and use BPM, which is booking per question. Think about this as an estimate of the expected revenue. And we plotted the mean square error as a function of how many demand function we are using. So what I have here is how many demand function we are using coming out of the clustering algorithm. And here is the mean square error for BPM and for QPM. Blue represents BPM, that's the left-hand side, that's like the expected revenue. And the red line represents QPM, that's like the probability of purchase. And you can see why we failed. We selected the number of demand function, which is the worst possible number of demand function, which is 10. And that's what we finalized. we need to increase. We selected between 90 to 100 event function. And the next set of results that I'm going to show you is application of this technique in a 6-month field experiment using this data. And I'm showing here the application to 5 different product deal category: beauty, food and drinks, leisure, services, and shopping. I should point out that beauty and food and drinks generate most of the revenue for Groupon, or at least at that time. Yellow represent booking, which is total revenue collected by the company. Does this make sense? And booking is very important because all these online retailers are focusing on market share. Booking is a reflection of market share. You can see that we did very well when you look at booking. In beauty, we increased revenue by almost 150%, for food by 100%, for leisure by 60%, for services by about 80%, and by huge amount for shopping. Blue represent revenue. This is what stays with Groupon. So it's booking minus what is transferred to the merchant. You can see we did well in beauty, we did well in food and drinks. We failed in leisure. We are neutral in services, and we are doing extremely well in shopping.
So, but David, one of the things I'm wondering about is they had an algorithm, which was this cost plus. How did it perform so well with so in other words, there was some logic in the amount of the cost plus they added.
So remember, I said these are data scientists. So they use historical data to optimize a fixed price strategy, and 10 generated huge error relative to what is true, and as a result, we are making wrong decision in the selection of the course.
Yeah, but I'm wondering about what they were doing. So they were using an algorithm, which was somehow using the empirical distribution
to have a fixed price. To have a fixed price.
But it's a markup, right? In other words, I'm trying to see why that logic dominated the 10, because there was some logic in what they were doing before.
So I'm trying to explain. Our 10 were generating the wrong forecast.
I see.
The wrong forecast take me in the wrong direction. Right? And this simple idea that I'm going to just to look at the historical data was powerful enough. As soon as we move this, you can see. So today they are using, or at least for a long time, they were using our algorithm, except under leisure. Leisure is a little bit tricky for us because my understanding is that when people buy a trip to vacation in the Bahamas, they do it 2-3 months ahead of time. It's very difficult for us to take into account the impact of lead time on the business. So that was the initial Groupon story. And we were working with one of my students, with Rulala, setting some algorithm for the initial price. And we said, okay, we have an opportunity to optimize on the fly prices for Rulala. But very quickly we realized this is not going to work. Why it's not going to work? Because unlike Groupon, Rulala has limited inventory. And when you have limited inventory, sequential learning and optimization is a challenge, because by the time you finish learning, you may have consumed all your inventory and there is nothing to optimize on. And so the question was, can we combine learning and optimization to improve performance? So here is the model. Very similar to the one before, with the addition of limited inventory. I have a selling horizon with T period. Think about a period as an arrival of a customer. I have limited inventory, and I have a discrete set of prices. Here are the prices that we can use. Under price PI, expected demand or the purchase probability is DI, but I don't know it. And remember, they are introducing many new products to the market with no historical data. Question is, how can I learn and optimize on the fly? Now, this problem, when there is no inventory limitation, is precisely the classical multi-arm banded problem. Right? In the multi-arm banded problem, we have a gambler sitting in front of slot machines. The gambler has a sack of coin. The gambler needs to decide which arm to push next, how many times to push it, when to switch, to which machine to switch to maximize his or her error. This is precisely our problem when I have unlimited inventory. For example, you look at this product where I'm considering 4 different prices. So in this case, a price is a noun. People coming in to the website are the coins. The retailer is the gambler, and the same question. Which price to introduce to the customers, how many times to introduce it, when to switch, and to which one to switch to maximize expected performance. Right? So this is the classical multi-arm blended problem, but with additional twist of limited set of resources, limited inventory. One of the very first algorithms that was developed for this problem is what is called now Thompson Sampling. How many of you heard about Thompson Sampling? I know some of you who know. So Thompson Sampling was initially introduced, is a very peculiar algorithm. It was initially introduced for drug testing, for the effectiveness of different treatment. And it was, Thompson was in the medical school at Yale. This paper was published in 1932. And it sat there for a very long time until about 2000, where people from Yahoo, Facebook, and Google started reporting that they are experimenting with the algorithm and it's working extremely well. And then people in our community and computer science started writing papers to explain why it's working well. So all the papers that were written up to this paper were focused on the unlimited resource case. So let me explain what Thompson sampling is all about, and you'll see it's actually a very strange algorithm. And what I like about this story is, and there is here a lesson for us as referees and editors. This is a paper written in 1932. If the referee said, what are you talking about? You cannot implement this algorithm in 32 because we don't have the data that you need, they would have killed probably one of the most important papers in the multi-arm blended context. So we need to think about this when we are rushed to say, oh, you don't have the data for this algorithm, it's not practical, we are not interested. Okay, so what is this Thompson sampling algorithm? Suppose I'm considering 2 prices for this product, the low price and the high price. Under the low price, expected demand is 0.6, but we don't know. Under the high price, expected demand is 0.3, and we don't know it either. What I'm going to do is generate estimators of the true expected demand from beta distribution. I'll have a beta distribution for the low price and a beta distribution for the high price. Notice that beta distribution is characterized by 2 parameters. I will always think about the first parameter is the number of successes I have with this price, and the second parameter is the number of failures that I have with this price. Okay? And because I know nothing, I will always start from the uniform distribution. Now, how does the algorithm work? Very simple. Customer arrive. I generate estimator from the current beta distribution. I treat the estimator as if it was reality. I will select the price that maximizes expected revenue based on this estimator. For example, suppose the maximizing is the low price, I will introduce the low price. Customers will make decision based on the true valuation, and the retailer observes this and updates the distribution. Does this make sense? So let's look at a couple of arrivals. The first customer arrives. I generate from the current distribution, which are uniform, estimator of the expected demand. In this case, P2, Tera 2 has higher expected revenue. Therefore, I will introduce to this customer the high price. The customer rejects, And as a result, I will update the second distribution for the beta distribution associated with the high price into beta 1 and 2. Now the next customer arrives, I generate from the current distribution. In this case, P1 theta 1 is larger. I offer the low price. The customer accepts our offer. As a result, I've changed the first distribution to be beta 2 to 1. And you notice that as I continue in this fashion, I'm starting to concentrate around the true demand function. Now, notice something very strange about this algorithm. If I wanted to maximize expected revenue, what I should have done, every time I generate the next price, I should have selected the next price to maximize expected revenue. Because I have a distribution of what I'm seeing now is the true demand function. But I'm not doing that. I'm flipping a coin to select which price to use. And the intuition why flip a coin is because I want to give the arm or the price where even if the likelihood is relatively small, I want to give it a chance to catch up and learn about its performance. Does this make sense? So the algorithm actually is not intuitive. Question is it effective? Right? And I mentioned earlier, it's actually quite flexible. It's easy, for example, to include the correlation between the different arms, different prices. It's simple to explain and to understand. And there were, as I mentioned, initially empirical papers reporting very good performance by people from, I think the first company were Yahoo and Google. And then people in our field are starting to write papers to say, yeah, we can explain why it is. Question is, how do you incorporate inventory constraint? Does this make sense? So our idea was actually very simple. We are going, remember in the Thompson sampling, we select the next price to be the one maximizing expected revenue, PI times theta. Now I'm going to solve an LP. What is this LP? This LP will have Xi as the probability to offer a specific price PI. Our objective is to maximize expected revenue, right? Subject to a constraint that says that expected sale is no more than the inventory, and subject to a constraint that says that the sum of the Xi is less than 1, and I'm going to reject a customer with the remaining probability. Does this make sense? Now you may ask yourself, why is he rejecting a customer, right? But that's, I'll talk in a few minutes why we are rejecting a customer. But that's basically the algorithm. Again, you can look at this and say, hey, something is wrong here. Why something wrong? First, you reject customer. And second, every time a customer arrives, you update the objective function. You update the left-hand side of the inventory constraint, but you are not updating the right-hand side. A more sensible algorithm may think about updating the right-hand side. And so the right-hand side will be the remaining inventory divided by remaining time. So I'm going to focus on two different versions of the algorithm. One is Thompson sampling fix, where the right-hand side does not change. Everything else changes, but the right-hand side does not change. And one is Thompson sampling update, where I update also the right-hand side. I want to see what the performance is. And we are focusing again on regret. So what is regret? For a given time, T periods and customer demand distribution, right? I am looking at the difference between expected revenue obtained by an oracle that knows the true probabilities of purchase, doesn't need to learn anything, minus the expected revenue achieved by our algorithm, depending on the version, that needs to learn about customer. Right? And a Bayesian regret is defined as expectation of all possible prior of the demand distribution. We basically solve the following, independent of whether you take Thompson sampling update, which is the more intuitive one, and Thompson sampling fix, for a model with T period and K different prices, the Bayesian regret is bounded by some constant times square root of the number of time period, and it turns out that square root of the number of time period is the best possible that you can achieve in terms of regret. And this result hold for any prior distribution of customer demand, and not single product, actually network revenue management setting, where I have multiple products, each product consume maybe multiple resources, and from each resource I have limited inventory. So think about the network setting. And now you can see why I may want to reject a customer, because maybe a customer wants a product that I can sell that they will purchase for a low price, but this product is using a component that is critical for a high revenue product. And so the setting with network revenue management with multiple products motivate rejecting some of the customers. The question is how good it is.
So here, even if you don't satisfy the demand, you still learn. Because
What does
the
it
customer
mean?
said, in other words, suppose you decide you're not going to use the inventory you reject
Meaning
the
I
customer.
reject.
Yeah, reject the customer. You will still collect the information from the customer, though you reject the customer?
When I reject, I don't offer a price, so I don't know how they will respond.
Oh, okay. So you give it the opportunity.
There is no cheating in the sense. I offer you a price, you say yes, I say no. If you said yes, and I offer the price, I have to give you the product.
So it's like you shut down.
I shut
accepting.
down. Exactly.
Okay.
But I shut down dynamically.
Yeah.
Right? David comes, he's a cheap guy. He wants this cheap product. Maybe should not give it to him because it will consume a resource or a seat from an aunt who may be willing to pay for another product a higher price. Does this make sense? So I'm doing it dynamically. Okay, so the question was how good it is. I'm going to show you here results relative to other algorithms that were developed for the same setting. There are basically two algorithms. The first one is by Asaf Zvi and Omar Best from Columbia University, where they do the sequential part. They start learning what I showed you for Google. They start by learning, then they switch to optimization. The intuition says, if you have limited inventory, it's not going to be effective, right? Because of what we talked about earlier. The second one is by people from Cornell and Microsoft. Their algorithm is actually similar to our algorithm. They solve the dual of our LP, but they use UBC instead of UCB instead of our Thompson sampling algorithm. And they have similar bound to our bound. So here are two examples. The paper has multiple numerical results with different types of data. I'll just focus on this. What I have here are two scenarios. On the left-hand side, I have a scenario where inventory is limited. On the right-hand side, we have more inventory. So what do I have? The x-coordinate in each scenario represent how many people arrive, right? T. And the inventory in the first scenario is 25% of the number of people that arrive. And in the second scenario, it's 50%, so I have more inventory. The y-coordinate represents performance relative to an upper bound on the optimal solution. Does this make sense? So the red represents the performance of Thompson sampling update. The blue represents the performance of Thompson sampling fixed. The purple represents the performance of the Cornell Microsoft algorithm, and the green represents the performance of Columbia University algorithm. You can see clearly that Thompson sampling dominates all of them. In particular, very impressive is with just 100 customers. Remember, you have only 25 units of demand. I am in the Thompson sampling update within 5% from the upper bound, not from the optimal. Right? It's maybe that the upper bound is 2% high. Now, when you increase the amount of inventory, everybody improves. Right? There is no question. The sequential will improve. Still, Thompson sampling, update or no update, dominates everybody else. Now, I want to bring to your attention this dotted blue line. The dotted blue line represents the performance of the original Thompson sampling algorithm with no domain knowledge. If you don't incorporate domain knowledge into the algorithm, you can see you're going nowhere. In fact, you are going in the wrong direction. This is one learning from this paper, how important it is to incorporate in this type of analysis specific domain knowledge if you want to achieve a significant result.
So in this case, the inventory constraint.
Yeah. In this case, the LP that takes into account all the inventory constraints. In the case, remember I mentioned this CPG company, when you do promotion, when you do just random forest, what you get is non-monotone relationship between them. It's not going to be effective, even if some algorithm says, this is the best way to predict customer demand. You need to adjust this in order to take into account the specific domain. Okay? Question on this?
David, question regarding when you run this algorithm and the recommendations are made, right? And somebody is implementing those recommendations, so it may be through an algorithm. How do they understand the logic of the algorithm? Because unless they understand the logic of an LP in which the coefficients of the objective and the constraints are changing, they wouldn't be able to understand.
Exactly. So it's a little bit easier in the sense that you can look at the dual of the container and give you an insight where it is going. But the implementation is automated way. In the testing, they want to see, hey, your algorithm is increasing, what is going on? Well, the dual gives us a lot of insight into what is going on.
So if you put this in a primal dual format, will it give any better results, or is there?
I don't know. It's a fair question. I don't know.
Because that one will tell me what is the shadow price of the inventory.
I don't know. We use this to tell us a little bit about what is the bottleneck and how to explain. But we use algorithms the way I explained it.
Okay. That may be also useful for somebody, manager, to know that what is the value of the inventory he has.
Oh, that's for sure. But that we use because we look at the dual variable. And also it gives you an insight into what is, I'm saying trivial stuff here in that respect. What is the impact of increasing your inventory by 5%?
But I'm also trying to understand this logic of turning away a customer.
Yes.
So you can estimate the value of turning away a customer, right? So it's almost as if before you learn from the customer, you're estimating a value to a customer, the marginal benefit of accepting the information.
So you don't have to assume. Let me show you a version of this algorithm that does not turn anybody.
Okay.
Let me show you a version. Okay. So the version of the algorithm is when David comes, who the algorithm wants to reject, I'm offering David the product at the highest price.
Okay.
It's clearly going to do what we are doing. So you for the proof of the nice theory, you can assume that. But from practical point of view, the result is going to be the same as I just said.
So the key would be that you in the Thompson sampling, indirectly, there's an exploitation component combined together.
Combined together.
Yeah, and so this would be the exploitation
power. So don't be misled by me saying that I'm turning anybody, because I can strictly improve and therefore achieve this result by saying, okay, when David comes, I'll offer David the highest.
No, but the reason I'm worried about this is the following. Let's suppose I'm the public, and I realize that the price I get and the timing and who else has bought is influencing what I see.
Yes.
Is there this is not a consideration here, but is there a notion of fairness with respect to this, or is it just the way you came too late, prices went up?
Well, but this is happening to you in the airline industry. We are just trained to think, but you're raising an important question, I'll come back to it. But in the saying of fairness, we go, George and I are traveling to China George bought his ticket because he has a very strong support here. At MIT there is no support. So he bought it, early on.
My fund is going to be gone.
He bought it early on. I'll pay for sitting next to him a much higher price. But there is a problem. The problem is, if you know what we are doing, think about the Groupon case, then you can influence my algorithm. How? You just, remember our algorithm is learning, so what you will do, you will just send back and forth, look and reject, look and reject. Our algorithm say, oh, demand is very weak, I'm going to reduce the price. So we solve this problem by looking, if David computer send 25 or 2,500 messages to the system, to the platform, we treat it as a single one. Right? We treat it as single. Now you can say, what are you talking about? We can have multiple computers, and you will not. So most people don't do that. If the Russian, but the truth is, if the Russian government is interested in beating Groupon system, they can do that, right? But I don't think the Russian government is interested in Groupon. They may be interested in other things, but no. Yes.
So David, so there was, I think, a recent paper that shows, so when these retailers all deploy these machine learning algorithms for pricing, right? So this dynamic pricing, personalized pricing, the algorithms can reach collusive pricing very quickly because they're in a lab setting, right? But at the same time, if you think about adversarial learning, so competitors, it is indeed, a customer is not going to go and do from distributed computing to sort of trick your algorithm, right?
Yes.
But a competitor can.
That's right.
Which is what is the click fraud in Google world with all the ads and everything, right? So
yes. So I can only talk about the setting I've been involved in. For example, the setting at Google. If somebody comes from the same computer and click multiple times, we try to eliminate. And it's possible, there are two things that are possible with competitors. One, they will try to trick us, it just doesn't happen. We have not seen it yet. It may happen tomorrow, but we have not seen it yet. The second thing that may happen is you're saying, hey, embedded here is what is the pricing of the competition. One of the features we are taking is the price. Now you may say, well, the competitor will change. It is possible and it will happen. So far we have not seen this happen. But these are all practical challenges. There is no question. Right? And I'll illustrate another thing. When we do promotion, remember competitor, when we do promotion for the CPGs that I mentioned, we do promotion, planning promotion today for 8 weeks from now. An important input for us is the competitor price, but there is no telling what the competitor price is going to be 8 weeks from now. So part of the machine learning algorithm is another machine learning algorithm that try to predict competitor behavior. It's not necessarily true that the competitor will follow what they followed before, but we definitely are assuming that they do. Does this make sense? So all these issues are out there.
So actually, if I was a competitor, rather than pinging you and not buying, I would spend a few bits of money to buy. So you will falsely assume demand is high, your prices will be high, and so it would be the other way around, right? I would spend a little bit of money to trick you into assuming that demand is high and then nobody will buy.
It can happen. You can, now that you know the logic, you can trick the algorithm. There is no question about that. Yes.
So, kind of question regarding, so it's a two-part thing. The TS fixed and TS update. It's single product versus multiple products.
So here I'm showing you single product.
Yeah, but does TS fixed make more sense when there are multiple products?
The results are exactly the same results that I showed you. The results that I showed in the previous slide are for actually the general setting.
Right. No, I mean, it depends on what you learn. So if for the purpose of learning, is it better to do TS fixed? And so if it isn't, the question I really had was that if you look at some of the other algorithms where we're saying there are lots of periods or lots of customers. If you think across products, is it possible to say that actually you can think of it as multiple periods, lots of customers?
So I don't know the answer to your question first, but I do know the following. We have scenarios where we experimented with multiple products, and sometimes TS fix does better, and other time TS update does better. From worst case point of view, the result that I told you holds. From the practical point of view, it's hard for me to say which one. And actually, when you look at our paper, you will see that the coefficients are different. Well, I'm hiding the coefficient, but the paper reveals the coefficient for TS fix and TS. And you see that some coefficient, the TS fix is better, other coefficient, TS update. I don't know what the answer to your question is. I would say empirical setting, I will test both to find out which one. Make sense? So I just want to highlight that this is really a general framework. This is not just the problem that I described. We extended the result to continuous price setting, right? Instead of assuming that you have a set of different prices, discrete prices, we extended it to situation where customers come with feature vector. So I learned a lot from the feature vector about individual customers. And then we extended it to what is called bandit with knapsack problem. Let me explain what it is by showing a special case where we tested our algorithm. And this is for display advertising. When you read the New York Times on your iPhone or your laptop, you will see a space where they put an ad. And suppose there are multiple companies that have different types of ads. For company 1, there are multiple ads. For company 2, there are maybe multiple ads. So think about, in the previous one, the arm was the price. Here, the arm represents the ads that I'm going to focus on. Each company has its own budget. For the next 12 hours, GM will have that budget, and Apple will have another budget, and so forth and so on. And your objective is to learn and optimize clicks, because you are paid based on the clicks. And so we basically show that the same type of result, the same type of algorithm work in this space as well. The point I'm trying to make, this is not just pricing. This is about general multi-arm vendor problem where you have all sorts of business constraints. So, questions. So let me take you through the third part, which is a deviation from everything that I described here, and also a deviation from classical learning algorithm. Typically, when we talk learning, we talk experimentation. My next question is, can we learn with zero experimentation? Right? And that's this learning from bundle example. This is work that was motivated B2W. We run, those of you who heard some of my talk, a lot of my focus with B2W was not on the learning from bundle. Learning from bundle came after. Was about the pricing like I showed earlier. You see similar results, so I'm not going to bore you with B2W pricing. But as we started working with them, we realized that there is another opportunity about learning that has to do with bundle. So let me, I talked about them, let me describe the motivation. I'm selling this product, Lemonade, for 10 cents. Customers are coming. 50% of them buy the product, 50% of them reject. I'm asking myself, what is the customer valuation? Can I say anything about sensitivity to price? Right? That's basically the question. Now, what I do know is that if the valuations are presented by this slide, 50% of the customers have higher valuations than 10 cents. As a result, they bought. And 50% rejected because the valuation is lower. But I don't know whether the valuation is concentrated. If I knew that it's concentrated, I would say, oh, this is very elastic. Small change in price, big impact on revenue. right? Or this is dispersed. It's not elastic. A small change in price will have very little impact. Does this make sense? So a single product, when I look at this with single price, it doesn't tell me anything. Now let's look at two products with a bundle. So I'm looking now at two products. Each is sold for 10 cents. And right now, for a second, there is no bundle, so there is nothing connecting the two products. As a result, if on the x-coordinate, I evaluation for product one, and on the y-coordinate evaluation for product two, there are 4 regions, it's trivial, right? Let's see what happens if I offer these two products also as a bundle at a discount of 2. If I offer the two products at a discount of 2, what happens? The buy both region increases, right? Increases to capture it. Question is, can I decode from this what's going on, right? All of a sudden we realize there is something going on here that maybe I can take advantage of. For example, suppose that I observe sales for the two products and I realize either customer rejected or bought the bundle. Then I tell myself, it must be that they are concentrated in this space. As a result, a small change in price is going to happen. Or suppose they are distributed everywhere. As a result, I tell myself, this is not sensitive that much to price, because they are all over the space, much like the previous examples that I showed. So basically, I'm going to try and figure out from customer purchase information about the individual versus a bundle, whether a specific product demand is sensitive to price or not. That's basically the idea. Question is, how do I do that? Okay. So here is our problem. Our problem is the reverse of the classical bundle problem, right? The classical bundle problem was introduced in the 70s in this paper by Yellen, who was the head of the Federal Reserve until Trump became the president. And she focused on, given distribution, what should be the bundle price to maximize performance. We are focusing on the reverse. Given price and sales for the bundle, can you decode what the valuation are? But our focus, as a model, will assume exactly the same assumption as in the bundle literature, right? That is, our model will assume unit demand when somebody purchases a specific product, and the valuation are additive and independent, okay? And the algorithm, basically, we show an iterative algorithm that finds the sensitivity by fitting intuitively a rectangle into the space of the valuation. Now, instead of describing the algorithm, I want to describe to you what we found through the algorithm in an intuitive, and then test whether this idea works. It's one thing to come up with an idea, it's another thing to see whether this works in practice. So here is an example to get ourselves a little bit more invested in bundle. So I have two items, item 1 and item 2. Each one is sold for a price of $10. And if you buy the bundle, you get a discount of $2. And on the right-hand side, you have information about sales. So item 1, we sold 40 units, item 2, 800, and the bundle 300. And my question to you is, which item is more elastic, right? Fairly simple. What's the intuition? I don't have a lot of information here, right? I have basically the sales data of the individual and the sales data of the bundle. So let's build our intuition and look at item 2. When item 2 was sold for 10 baht, we sold 800. But when item 1 was offered as a bundle with a discount together with item 2, not many people jumped to buy item 1 at a discount. So that tells me item 1 is not elastic. let's do the reverse. When item 1 was offered by itself, 40 units or so. But when we offer item 1 and we suggest, oh, buy also item 2 at a discount, lots of people jumped for the bundle, therefore item 2 is sensitive, right? And you can see this by fitting this rectangle. Again, now the area in each space represents sales. So here the area should be 800, here the area 300, and here the area 40. And if I try to do best fit for this rectangle, I see that the y coordinate is very narrow and the x coordinate is very wide, suggesting item 1 is inelastic, but item 2 is elastic. Right? Question is, how do I take this idea to the next level? Now, this insight was developed after we developed the algorithm. So let's see how we can. So this is an expansion of what I said. I did. Let's see how we can develop an indicator of which item is more elastic, based on the ideas that I just described. So I'm going to look at each item and calculate what I call the fraction of items sold in a bundle. So let's look at item 1. From item 1, I sold a total of 340, out of which 300 are in a bundle. That tells me, because the fraction is very high, that item 2 is elastic because lots of people jump to buy item 2 when it was offered at a discount with item 1. So item 2 is elastic. Let's look at the percentage of bundle for item 2. I sold a total of 1,100, only 300 in a bundle, which tells me that when item 1 was offered at a discount, once I sold item 2, not many people jumped. As a result, item 1 is inelastic. Does this make sense? That's really the intuition. The question is, you come with intuition, somebody else will come with different intuition. How do I test that this insight is correct? So the process was, here is a problem, we develop an algorithm. When we look at the algorithm, remember our discussion about interpreting the algorithm, we realize this measure is a measure of, that give us an insight into elasticity. How do I test it? So let's take data from B2W now. So I'm looking at two products, pressure cooker and recipe book. By itself, the pressure cooker is sold in typical weeks for $270. Recipe book for $40, and as a bundle for a discount of $9. And you can see the weekly sale, so the average weekly sale for the cooker is $222, for the recipe book is $30, and for the bundle, the average sale is $29. And the question is, which one is more elastic? So let's start with the recipe. The recipe book by itself sold 30. By itself sold 30. When we offer the pressure cooker together with it as a discount, lots of people, 30 people jumped to buy it, which means that the pressure cooker is more elastic. Let's do the reverse. Pressure cooker we sold 222. When the recipe book was offered as a discount, very few joined. So this suggests the recipe book is inelastic. And you can see our measures that I told you capture this. So if I look at pressure cook, the percentage of bundle is about 10%, meaning the recipe book is inelastic. The other product is inelastic. Reverse. The recipe book percentage bundle is almost 50%. This suggests that the pressure book is somewhat more elastic. These are all numbers. How do I test? We had an opportunity because during Black Friday week, B2W sell at a different price. So now I have two data points. And you can see their price during Black Friday. Pressure cooker at a discount of $17. Recipe book at a discount of $11, and there is no bundle. And you can see sales during Black Friday week. 1153 and 176 for the two products. I calculated the elasticity value, and the price elasticity for recipe book is 2.5, and for pressure cooker is 45, in line with what I showed you earlier. The question is this true only for this, or it's true across product? So this is what I'm doing here. I took a lot of the product, here is a subset, and each dot here is a product that was sold individually and as a bundle. Okay? The Y coordinate is the elasticity from the Black Friday analysis. Does this make sense? So this is what we trust is a true elasticity. The X coordinate is our estimator of whether it's elastic or not. How did I calculate the estimator? Take a product, take this product, look at all its partners, where it's sold with partner as part of a bundle. For each one of the partners, I calculate the percentage bundle, and if there are multiple partners, I just take a weighted average of all of them. Does this make sense? And you can see this beautiful correlation that is coming up between the two. In fact, look at the book. Black Friday suggests very little elasticity. Our results suggest very little. Look at pressure cooker. Black Friday suggests higher elasticity. Our results suggest higher elasticity. And we also apply a statistical test to test whether we can accept or reject the hypothesis of correlation.
So, wondering if you have underlying, I mean, there is data which is separate, but does this require an underlying assumption about the, because
Very good.
I really don't know who switched.
Yes. So,
It could be the opposite.
say it again?
It could have been the opposite, even though 40 and 800, right?
Yes.
It may be that actually a competitor offers it at $1 less,
Yes.
and therefore everybody switched when I offered it at $2 less.
Yes. So the underlying assumption is initially we assume uniform, that's why this beautiful rectangle, but then we generalize the result to a large class of distribution. So you need an assumption of the distribution, there is no question about it. But the algorithm we prove converges to the optimal under general assumption of the distribution. Okay? And just to highlight, if you don't use our indicator, you use a different idea to say, forget about the percentage bundle of partner. For each item, I will use the percentage bundle of that item. Does this make sense? Instead of the complementary item, you can see that you reject the correlation between the actual elasticity and the indicator of elasticity.
David, a clarification. So these are all with only one partner item?
No. This is why I said average. So here is a product. Let's say it's this guy. It's sold, say, in one bundle with 5 other products, and in another bundle with 7 other products. I take each one of the partners. There are 5 here and 7 here. I calculate the percentage. Then I take a weighted average. Okay? Yes.
So when we think about a bundle,
I can.
sorry. So when you construct the bundle or observe the bundle in the data, do we need to consider the relationship of those two products? So for example, in the previous example, the cooker and the recipe, one is the primary product, the other is like accessory, so there's some complementarity.
Yes. So when we selected this product to test, we selected them independent of assuming complementary or not. Okay? The beautiful thing about bundle, now this is not us, is that you can show the value of bundle. This is not our work, this is earlier work, even if they are not complementary, completely independent of each other, which is very surprising. I have 2 products that are completely, where the valuations are completely independent, and it's better to offer a bundle because it increases expected revenue. This is not us, So this was done in the initial work. What we are showing is, give me a bundle, do this, I can show you an intuition about.
Will that relationship contaminate your prediction?
So some of them, maybe, some of them are complementary, some of them are not here. That's what I'm trying to say.
So the question would be, are you making an underlying assumption that the valuation is additive?
Yes, I made 3 assumptions, not one. I tried to mention this at the beginning. I'm making one, unit demand, so when you buy one. Second, valuation are additive, absolutely. And third, they are independent. So the point is made. So I'm assuming independency, but as is pointed out here, there is no telling independent or not when I look at the data. Right?
But as long as you assume additive and assume that the general distribution for the valuation of a random vector, so all the products that I'm interested, why wouldn't this method work? Why would you work? Why wouldn't this method work? Maybe slight modification by the fact that there is dependency.
Yes.
Essentially, you are sequentially classifying upper
Yes.
sets and
Yes.
sets associated with classifying these probabilities.
Yes. So I don't know if you relax the independency. That's what you're talking about.
Yeah,
actually.
yeah.
If it works, I have no idea.
The algorithm
It's-
has to be modified because
Yes.
the way it is
Exactly.
computed.
Exactly.
But
It may be that if you include dependencies, that a different version of this algorithm.
because yeah, this can be the.
But the point I think that both of you are making. I mean, we did not. I have no idea about this idea whether they are independent of each other, like our assumption, or not. But I do know that the correlation is very strong, right? Which may suggest, following this comment, that maybe there is a way to adjust the algorithm to deal with it. I have no. Okay? So let me, and that's what the algorithm basically uses. It uses this parameter. So remember, I'm showing you the insight and the punchline, but the way it was developed is different. First, we look at data, we say, oh, for these guys, maybe we can learn. Second, we developed the algorithm, and the algorithm told us, look at this one, which is really a nice interpretation. Let me just summarize by highlighting a couple of things. I think, and my understanding is that you, this group here, and this school, and maybe the university, is moving in the direction of data-driven, both in teaching and in research. I want just to emphasize that we are dealing with systems, I mean, you know, that involve people without real data. It's hard to understand behavior, right? And by the way, and I should have added a slide on this. This is why we have a new department at Management Science looking at big data, and this is why George and others are running a special issue to motivate this type of research. The second observation that I want to make is that this kind of data-driven research, I believe, help us come up with new both engineering methods, these are the algorithms, and new, what I call here scientific methods, think about them as laws of physics, right? That help us achieve the objective that I started with, which is explain behavior, predict behavior, and maybe change behavior if we do our work right. But to me, the final thing to say is that it's important to integrate a domain knowledge into this type of work, because otherwise you probably are going to come up with the wrong conclusion. And there is a lot of debate now, even in the AI community, about the importance and the impact of domain knowledge. At least our experience is that this is a critical part of the work. I should point out just that there are a couple of papers. I think I sent some of them. One is a paper with, all these papers are with former PhD students who recently graduated. Wan Chi is now on the faculty at NUS, and He Wang is a professor at Georgia Tech. This is the Groupon paper. Then there are a couple of papers based on the Rulala work. Chris Johnson is now on the faculty at Harvard, and again, He Wang is at Georgia Tech. And the bundle is with another student, Wilma, who just graduated and is joining Columbia University Business School. And I will stop here and see if there are comments.
Any other questions?
I have one question. So when you talk about the bundling phenomena, so the example you showed, like the sales increase in the Black Friday week. So how do you interpret or take into consideration any other factor due to which this might be the phenomena and not just because of bundling?
I'm using the Black Friday just as an indicator of what the elasticity is. I didn't take any other factors.
Like, but there could be like some factors like the competitor might have sold out or it might have stock out or some other factor.
Like was the point that was made earlier, all could be. But still, with all of this, you see what comes out of the algorithm and you see that it's consistent with the elasticity. You tell yourself something is embedded here that is giving us this. And that's the kind of insights that we provide our partners.
No other questions? Let's thank David. Thank you. A little bag for you to carry along back to Boston. Thank you again. Thank you.
Cut.